is life and lots of carbon, because that's true. Organic molecules are complex molecules, which is to say they can be very, very big and very, very complex, to an extent that you have molecules inside of you that are designed to respond to an electrical signal and cause movement in your body. It's an incredibly complicated molecule. There's crazy things going on. Actually, there's a bunch of molecules involved. The molecules that make up, say, like your DNA, which is a single molecule that, if stretched out, would be, visible in length. 5-10 centimeters each chromosome if stretched out, which is crazy when you think you've got 46 of them crammed into each cell in your body, and you've got trillions of cells. Big, long, complicated molecules. Basically, anything in a cell that's a molecule is an organic molecule, and they all have really specific functions. And to have specific functions, just like anything else, they have to have specific shapes and designs, right? So how do you take carbon and turn it into, one molecule you'll learn about if you take biology, which is a gate that spins as hydrogen ions flow through a channel and makes a new molecule. How do you build something like that? That's a big, complicated gate, right? But if you learn about ATP synthase, that's exactly what it does. It's designed that as a hydrogen ion flows through it, this thing spins around and literally is responsible for making other molecules. One molecule whose job is to make other molecules. That's complicated stuff. How do you build something like that? And the answer is, just like with your Lego blocks, if you were trying to make a big, complicated structure, would you start with all of the little Lego pieces that are just two, does anyone know what they call the little studs? Yeah, so would you start with just those little double pieces and try to build a complicated thing out of that?
Oh, you could.
Not complicated.
Not complicated, right? If you want to make something big and complicated, you're probably going to want to pick the Lego that can make lots of connections, right? Does that make sense? And likewise, when we go to make complex molecules, we want to pick atoms that can make lots of connections to be the spine of that thing. Does that make sense? Because if we pick atoms that can make lots of connections, we can make them into lots of different shapes. If you think about hydrogen, you're not going to make big, long, complicated shapes out of it because it can only make one bond. So you take one hydrogen, you connect it to another hydrogen, and you're done. Nothing else you can do. You got hydrogen gas, and you're done. Even oxygen can only make two connections. So you take oxygen to oxygen to oxygen. Now you've got a chain, but can you attach anything to that chain? No, it's used up all of its bonds just in connecting to itself. So what we end up making big, complicated molecules out of is what? What atom is a good candidate? Carbon. Silicon's actually a really good candidate too. You'll always see in like science fiction movies, they'll talk about like silicon-based life forms. And that's actually, there's some good science in that science fiction, because even though life on our planet has carbon as its backbone, silicon has similar characteristics. It would also be a good candidate for making big complex molecules because it also makes 4 bonds. Silicon's also pretty abundant. It's not as abundant as carbon, but the big one on Earth, the big one in life as we know it, is carbon. And carbon is ideal because it can make 4 bonds, which means you can make a chain out of carbons, one connected to another, connected to another, connected to another, and every one of those still has 2 more bonds it can make, which means you can make a chain and then have a chain come off of that, another one here, and you can connect different things. You can put hydrogens here, you can put whatever. Does that make sense? Yeah.
Wouldn't that not work very well if you have, like, say, a carbon double bond with a carbon, that's double bond with another carbon, and all the carbons are double bond?
Well, of course, like anything else, but we also don't want, when we build something, we don't want to go on forever, right? So at some point, we're going to want to stop it and have it be of a finite size, right? And so that's, you're right, double bonds is one of the ways we do things like that. And we'll talk more about that. So in general, when we talk about organic compounds, there's exceptions, but most organic compounds are made on a backbone of carbon. And I think I said that up here. And the other thing to keep in mind is this: if we don't want this thing to get out of control, just like Alondra said, carbon can make 4 bonds. Are you missing the note? Right here.
Oh.
That's okay. I gotcha. There we go. So carbon can make 4 bonds, which makes making a chain very easy. But sometimes we need to stop the molecule. So in other words, I don't want to do carbon and then connect a carbon to each of these. Don't draw this. And then connect a carbon to each of those and keep going. That would give me like graphite or diamond or other forms of carbon, but that's not an organic molecule. I want to shape it and sculpt it and have it move in certain ways. So when I want to stop carbon from spreading, what is the most abundant element in existence that will also serve to cap this thing off? Hydrogen. So anytime we want to rein this thing in and stop it from spreading, the most logical thing to put there, and again, we're talking as if, you know, every one of these molecules is being built by some designer, like, you know, with tweezers, but it's helpful to think that way. Keep in mind, that's just a way of thinking about it. We will later on in the course, give me just a minute, okay, I do want to answer, but let me finish this thought. We will later on in this course talk about not just how they work like we are today, but why certain things form when they do and why certain things don't. But for now, if we're imagining designing this, if we put hydrogens on, anywhere we put a hydrogen, it just stops, right? It can't make any more bonds. Very good. So the backbone is carbon, and sort of the border, the boundary, the outside edge of all these molecules tends to be hydrogen. That makes sense? Carbon lets you keep going. Hydrogen lets you stop. So by default, we make chains out of carbon, and anywhere we don't want something specific, we put hydrogen. And it has other properties. Carbon-hydrogen is a pretty boring bond. The difference in electronegativity is slight. It's a stable bond. Nice stable bond. The other thing to note, what's the hybridization state of all these carbons by default? sp3. So we can mention that too. How to stop? Hydrogen. And it defaults to sp3 hybridization, which means that weirdly around this carbon, we would actually have a tetrahedron, right? But then this carbon would also have a tetrahedron around it. So this is 109.5 going down. This one will then have a bond of 109.5 going up. And this one will have a bond of 109.5 going down. And as the chain gets longer and longer, even though none of the bonds is straight, we get a straight line. It'll look kind of like this. That makes sense? Yeah. Yep, absolutely. And each angle should be 109.5 by default. Does that make sense? Okay, so organic chemistry at its most basic, and this is all we're going to talk about today, is just chains of carbon. When we want to then have those chains of carbon do specific things, we'll throw other stuff on, and we're going to talk about that in coming days. But it all starts with chains of carbon. And of course, you know from van der Waals forces that as we change the length of those chains, some of the physical properties will change, right? If I wanted to make an organic molecule that would be a gas, I would make the chain small, short. If I wanted one to be a liquid, I would make it longer. And if I wanted it to be a solid, I would have to make it really long, right? So chain length is the first thing we're going to talk about. The first part of an organic molecule that determines its physical characteristics is just how long the chain is. What is the simplest chain imaginable? Not the name, but just what would it look like? The simplest organic molecule.
One carbon with 4 nitrogen.
Very good. Like that. And I probably shouldn't have drawn it enormously, so it spilled out into the surrounding space. But yeah, that would be the most basic possible organic molecule. 1 carbon, and then to make this thing stop, hydrogens. Hydrogens are terminal, right? They end things. The formula of this obviously is CH4. And what do we call CH4? Methane. Very good. Now, what is the next most complicated organic compound? 2 carbons. So we'd have carbon attached to carbon, and obviously hydrogens. So we would draw it like that. 2 carbons. Its formula is what? C2H6. Good. That grade 9 patterning to algebra you did, it should start jumping out at you now. See if you can figure the equation out. But I want to show you something else. You know how we draw this? Oh, that was anticlimactic. You know what? The anticlimax is my specialty. We draw it like that. Here's the deal. In organic compound, this is the full drawing. This is correct. But you can imagine as these get long, holy crow, will drawing a million carbons get exhausting. We could also draw it like this. These are all accepted ways. The line, here's the deal. This is actually the most common way in the middle. All we do is we draw the bonds. Anywhere a bond ends, unless it says otherwise, we assume that's a carbon. And then we assume that hydrogens fill in all appropriate gaps. Does that make sense? We'll talk about that more. But this is called a skeleton diagram. And all we draw is the bonds. And anything that isn't a carbon or a hydrogen, we'd put that letter. Like if they threw a nitrogen in there, then you'd draw the bond and put an N at the end. But if there's no letter, we assume that each bond is, ends at carbon. And we assume that each of those carbons is stuck to as many hydrogens as it can be. And don't worry, if that seems confusing, you'll get tons of practice. And I promise you will want to draw them this way, not this way. I promise. Am I right? Yeah, I'm right. Because this gets old really quick. What is the next most? Oh, does anyone know the name of this? Very good. Ethane. Isn't that creative? Methane, CH4. C2H6, a 2-carbon chain, is called ethane. Isn't that right? Now, the next most complex would obviously be 3 carbons, right? And at this point, I'm not even going to draw the hydrogens here just for space purposes, right? We understand that hydrogen exists everywhere. How would I draw this as a skeleton diagram? That first line is a carbon to a carbon, and now I need to go to another carbon. And of course, it's sp3 hybridization, so that angle's going to go down like that. That make sense? So this really means carbon, carbon, carbon. And on all of those carbons, oh, I'm feeling guilty. I'm going to draw the hydrogens. I couldn't hold back my guilt. And on, but see, do we see how much nicer this is? And if I wanted to draw it, the first one would be CH3. What is the next one? CH2. And the last one? CH. Good. These are all acceptable ways of drawing that. Again, what's my favorite? Very much the one in the middle, right? But it takes some practice. The formula for this. Very good. And what's it called? Thane? That's good thinking. That is propane. Good. Very good. All right. What would the formula of the next one be? C4, H10. And this one, I'm not going to draw all the ways unless you really want me to. I'm going to draw it like this. We started a carbon. We go to a second carbon. Now I need a third carbon. And now a fourth. So again, it's at the end of each bond. There's a carbon. And of course, each carbon is attached to as many hydrogens as possible. If I wanted to draw this like this one, the first carbon would be CH3. What about the second one? How many hydrogens would it have? 2, because it's already making 2 bonds, right? So CH2. What about this carbon here? Very good. And the terminal one, the final carbon? Very good. And what would we call this? Does anyone know? Methane, ethane, propane? You might have a lighter with this in it. Butane. Very good. Hey, what do you notice about all of these words? They all end in ane. Good. That ane ending tells us that's a chain of carbons.
Really?
And the prefix tells you how long that chain is. Makes sense, right? Okay, we'll speed things up a bit. The next one obviously will have a formula of C5H12, methane, ethane, propane, butane. And now the names get predictable. They get better. Because 5, very good. Pent, what? Pent? Ane, pentane. Good. And 1, 2, 3, 4, 5. Right? Again, the end of each bond is a carbon. So 1, 2, 3, 4, 5. And I'm going to give up on even doing these longer ones now. Is everyone comfortable with that? Tell me if you're not. Okay, what's the 6th one going to be called? Hexane is correct. What's its formula going to be? Yeah, I like that. By the way, what is this pattern? Has anyone caught on to it yet? Sorry, what is it?
Means +1 carbon +2 hydrogen.
Oh, okay, yeah. So if I wanted to generalize it, I could say however many carbons there are, how many hydrogens will there be? Twice as many +2. Good. That's the rule of thumb. We're not going to do any math with that, by the way, but just if you're wondering, if somebody said, like, hey, what would a 15 carbon chain look like? Well, there'd be 15 carbons, then there'd be 32 hydrogens, right? You double it and you add 2. And you add 2 because the end carbons always have that one extra hydrogen, right? Because that's where the chain is stopping. What would this one look like? 1 carbon, 2 carbon, 3 carbon, 4 carbon, 5 carbon, 6 carbon, right? Again, it's not, the line isn't a carbon. The line is a bond. At the end of each line is a carbon. And then those carbons are stuck to as many hydrogens as they need to terminate, to not keep growing. All right, after hexane, this one's weird, I guess. I said they were easy after this, but this one's a little weird. You'd think, but they go back to the Latin, actually, and it is heptane. C7H16 is correct. 1, 2, 3, 4, 5, 6, 7. After heptane? Octane. Fantastic. After octane? Nonane is correct. Well done. After nonane? Decane. Good. And they don't do the X, though the X would make sense, but they do the C. So octane will have a formula of C8H. Great. 1, 2, 3, 4, 5, 6, 7, 8. Take a few seconds and fill the rest of the chart out. All right, showoff.com. Wow, it's nice of you to have timed it to the 10th of a second. That's incredible. That's a good question, actually. I guess it would be a decisecond, which sounds very, very strange. But it was nice of you to measure it to the nearest decisecond. Thank you for that.
It sounds like you're trying to say like
All right, how are we feeling? This isn't so bad, right? The naming system The naming system's a little weird. It's probably not what you'd come up with if you were starting from scratch, but once you get used to it, it works. And you're going to see that over the next bunch of days, we're going to learn to name really complicated things with great, really wonderful, long, confusing names, and the name will make perfect sense to you. All right? Oh, it really will. It really will. So the name here just tells us how long the chain is. Now, of course, a chain could have, the whole point of this is that we don't just make a straight chain. Once we make a straight chain, we could add branches, right? If you look here, what do we see? We see a straight chain, and then we see it's got some branches. So how do we name this? Well, the first thing we want to do is we want to find the longest possible carbon chain. And most often, wow, that really just washes right out. Oh, it's been so long since I've complained about the colors on my projector. You know, on my screen, they look so nice.
Really?
Yeah, it's amazing.
Maybe you just need to
So usually, yeah, they make the longest chain here. Do be careful. Sometimes you have to follow a branch to get the longest chain. In this case, it's the first one we've ever seen, so the longest chain is just this. Does that make sense? So right there, how long is this chain? 1, 2, 3, 4, 5, 6. What is that chain? What's its name? What is it? Hexane. Does that make sense? The longest chain is 6 carbons, which means that this chain is hexane. When we name organic molecules, the names are instruction manuals. Built right into the name, it tells you exactly how to build the molecule you're trying to build. So in general words, I would say we're making hexane, but what do I have to add to that hexane? What does it need?
It would maybe include hydrogen.
No, I don't even mean that. We don't even think about hydrogen because hydrogen just fills in the gaps. Everywhere we need this thing to stop, we put a hydrogen. So the naming doesn't think about hydrogens because there's millions of them. And if we started numbering the hydrogens, we'd go crazy. So it's good thinking, but it's for somebody much smarter than I. I can't keep track of 18 hydrogens, though you're not wrong. Like it does take that many, but just really quickly, I'd say I need hexane. I need a 6 carbon chain, and then do what to it? More specific than that. Because I could put 3 more carbons in there real easy, right? But I could do it a bunch of different ways. I could have put 1 on a bunch, right? That's not specific enough. So don't count the hydrogens, that's too specific, but I need to know where those carbons go. So I need something in the middle of specificity. What would I say about this? Just in everyday language, make a 6 carbon chain. If you were trying to tell somebody to draw this. In a straight line, okay? And then do what with it?
Add a carbon on the second carbon.
Good. We need to add 1 carbon on the second carbon. That's this group here. Add 1 carbon on carbon 2. And what else do we have to do? So we add 1 carbon on carbon 2, but there's still another thing to be done, which is what? Very good. And then we're going to have to add 2 carbons to carbon 4. And the way we do that is this. 1 carbon, what do we call a 1 carbon chain again? Methane. So this is a methyl group, right? We're adding a 1 carbon chain. So when we add methane to a chain that's already there, we say we're adding a methyl. And if I go to add a 2 carbon chain, this will be called an, not propyl, propyl would be 3, but good thinking. Ethyl, good. And then you're going to see, you're going to like this naming because it's super specific. Ready? So there's a methyl on 2, and there's an ethyl on 4, right? Does that make sense? And what that means is there's 1 extra carbon coming off of carbon 2, and there's 2 extra carbons coming off of carbon 4. And then we put these in alphabetical order. So don't write this yet, okay? I'm gonna give you all the time you need, but I just want you to follow what I'm doing first. So we would call it this. We put them in alphabetical order. So which one comes first? So we would say it's ethyl. Don't write this yet. And then methyl. And then the thing itself is called hexane. Now, the only information missing is what? I need to know where to put the ethyl, and I need to know where to put the methyl. So we just put those numbers in. What carbon is the ethyl on? So we say this is a 4-ethyl 2-methyl hexane. Right?
Ethyl sounds like a name like thing your kid can't do.
Or ethyl 2.
But not as much as you hated the kid you named methyl. To say nothing of the kid you named butyl. So, and if any of you has an Uncle Butyl, I apologize. But his name sucks. So, or her. So, I want to be very clear. We only put dashes where numbers meet words, and it's one word. That is one word. There's no space in it. That is 4-ethyl 2-methyl hexane. That's a word. 4-ethyl 2-methyl hexane.
So
One word.
we can make the longest word.
If you wanted to name your child 4-ethyl 2-methyl hexane, he would probably be the only 4-ethyl 2-methyl hexane on his attendance. And you'd never have to worry about them being like, 4-ethyl 2-methyl hexane, are you here? And they'd be like, do you mean 4-ethyl 2-methyl hexane B or 4-methyl 2-ethyl hexane F? All right? And then it's always like, now what are we going to do? I went to school with 2 Megan Elizabeth Ryans. What do you do with that as a teacher? Right? Like, same first name, same middle name, same last name. You're done.
Just Megan 1, Megan 2. What became here first?
We called one of them H because she was Megan with an H. And we called one of them A because she was Megan spelled M-E-A-G. So we called them H and A. So imagine being given a lovely name like Megan and then for the rest of your life being referred to as H. That's or A. It's very disappointing. But there you go. So 4-ethyl 2-methyl hexane. Does it make sense? It is just super descriptive, right? It is an instruction manual in a name. How do I make this thing? Well, it's a hexane. So I'm going to start by making a chain of carbons that is 6 long. And then what am I going to do to it? Well, on the 4th carbon, I'm going to put 2 carbons coming off of it. And on the 2nd carbon, I'm going to put, which is 1 carbon. By the way, if I wanted to draw this as a stick drawing, I start with the main chain. So how long is the main chain? So I'd go 1, 2, 3, 4, 5, 6. And then what do I have to do with this? Sure. So on the first thing is 4-ethyl. So on carbon 4, 1, 2, 3, 4, I have to put a side chain coming off that looks like that, right? 2 carbons. What else do I need? Yeah. So I go to the 2nd carbon and I put a chain coming off of it. That's the stick diagram of that. Those show the same thing. Stick diagrams are weird at first, but I think we can agree this is a lot easier to draw than this. This is some. As a rule, go away from the chain, not into the chain. Sometimes you'll have to do both if something has 2 subchains coming off it. But as a rule, don't go into that space there. Go outside of the plane. So if I was coming off this one, I would go down. Right? Just go away from the middle. So you have more space. And that's just a drawing thing. Okay. So this is the basic idea. And the other thing is this. Of course, you could start counting in either direction, right? Like if you look here, I could count this way with this as 1. Why did I choose to start with that as 1? Why do you think? Yeah, because it's easier. Oh, I mean, that is 1, that is 1. I'd argue that numbering left to right is probably easier. It's what we've been doing our whole lives. If you look at these, I've pre-numbered these for you. So I've said this is the main chain. How long is the main chain?
Oh, I always get my left and right with stuff. That's why I was confused. I was like, I don't think numbering it that way.
Yeah, so this is I agree. So this is a heptane. I'm going to leave myself some room. And I numbered it this way because one of the principles is number it so that the side chains have the lowest numbers possible. Does that make sense? If I called this 1, then carbon 1 has no side chain, carbon 2 has no side chain. We have to wait until we get to the 3rd carbon to have a side chain. Whereas if I start numbering over here, I already get my first side chain on the 2nd carbon. Does that make sense? So we always number it so that the lowest number has a side chain. Okay, so let's talk about the side chains here. Do we have any methyl groups? How long's a methyl again? We have 3 of them. We have 1 on 2, we have 1 on 3, and we have 1 on 5. Okay, you guys can do this. Ready? We have 3 methyl groups. So how do we say that? Am I going to say 2-methyl, 3-methyl, 5-methyl heptane? That's long. I could do it, but that's long. So what am I going to say? We have 3 methyls, and they're on 2, 3, and 5. So how are we going to say that?
Methyl 2, 3, 5, or 3 methyl 2, 3, 5?
Close. We're going to say 2, 3, and 5, because that's where we find them. And then I want to say that there's 3 of them. What's the prefix we use for 3? Tri. Tri-methyl. That's what that gives us. So that's going to be part of the name. What else is on this? So I have 3 methyl groups, and I have... That's right. I have not propane, but I have a propyl group. Propyl. And specifically, what carbon is it on? So I don't just have a propyl group, I have a 4-propyl group. And other people do it differently. I always mark up the diagram before I start naming it. Does that make sense? So I know I know this thing is a heptane. I know that it's got methyls on 2, 3, and 5, and propyls on 4. Now remember, they go in alphabetical order. So methyl starts with M, and propyl starts with P. I know this is tri, but we don't base it on tri. We base it on methyl. So which one should I list first? The methyl group. So what will the name of this be? Who wants to be brave? Worst case scenario, you're wrong. Yeah, take it away.
2, 3, 5, 5 methyl. 4 propyl heptane.
Very good. It's a crazy name, right? But this is nothing. It's actually not true. They don't get much longer than this. That's about as long as they get, because when they get a lot longer than this, we have new naming systems to make it shorter. So this is getting up there in length. They get more complicated in this in content, but not in length. That's a pretty lengthy one. So 2,3,5 trimethyl 4-propyl heptane.
That's not fast.
No.
You say that 5 times fast.
Okay, this guy here, let's identify the longest chain first. How's the longest chain going to come at us? So we could start here. That would be 1, 2, 3, 4, 5, 6. I think we can do better than that. I could go here. That would be 1, 2, 3, 4, 5, 6. I think we can do better than that. If I go here, it's 1, 2, 3, 4, 5, 6, 7. So I think that's my longest chain. Hey, what is this thing? It's a heptane again. Yep.
What if we go the opposite way to like collect numbers?
Well, that was going to be my very next question, Alondra, so thank you. Which way do I want to number this?
Like to left?
Yeah, and why do I want to go right to left again?
Because the smallest numbers are like the opposite is what it usually will say.
Good. So if I went this way, 1, 2, 3, 4, I don't get my first chain, my first group, until carbon 4. If I go this way, 1, 2, 3, I get my first group on carbon 3. That's better naming. By the way, if you named it backwards, I would still figure out what you're trying to draw. That's not the best name. The best name has the lowest numbers possible. Does that make sense? So you can have multiple names that are right, but the best name is the version of it that keeps those numbers as low as you can. If you occasionally get one wrong, as long as what you said still makes sense, I'd probably give you the mark. But don't make a habit of it, because if you did it twice in a test, I'd notice. If you did it 4 times in a test, I'll start dinging it for you. Does that make sense? So you'll probably miss it once in a while. I will miss it once in a while, and you'll go, oh, Orlando, couldn't we actually do the numbers lower if we counted left to right? As a rule of thumb, we want to keep the side chains with the lowest numbers we can. So we'll call that 1, 2, 3, 4, 5, 6, 7. Hands up, please. Who can give me the side chains we're dealing with here and tell me how to name them? Who wants to be brave? Yeah, Zach, go.
For the first, the one on the 3 and 2, well, I guess I'd say that's 3 dimethyl.
Ah, good. So dimethyl, I like that. The problem is you can't just tell me where one of them is. You have to tell me where both of them are. So it would be a 3, 3 dimethyl. Okay, and that's very specific, right? So that tells me that on carbon 3, there's a methyl, and on carbon 3, there's another methyl. Does that make sense? Who else wants to give me some naming here? Yeah, Alondra.
4 ethyl.
Very good. So we can also say that on carbon 4, we have an ethyl group. So we can call this 4-ethyl. Hey, when I go to put these on the name, what order will they come in? Ethyl and then. Very good. Jay, do you want to try the whole name? No? Okay, who does? Oh, someone new. New faces. The worst case scenario is you're horribly wrong. Kevin, go.
4-ethyl 3.
Very good. There we go. 4-ethyl 3,3-dimethyl heptane. And again, this is a fairly complicated one, but it's legit. By the way, where's my remote? Just to show you, what's this thing called again? Yeah. We'll give that a minute to load. I'll do the next one while that loads. Okay. I want you guys to try this one. Try this one. Ah, now no matter what you do, it's going to be on the 3rd carbon, right? Ready? What we want to do is, since we have to keep the numbers as low, the numbers are the same either way, we want to pair the lowest number with the lowest letter alphabetically if we can. So when in doubt, if it's a choice between 3-methyl or 3-ethyl, we're going to pick 3-ethyl. I will not get super hung up about that. All right, I will not. But we favor the lowest letter with the lowest number, all things being equal. Again, I'm not going to be super strict. Well, is that a lie? I might be. I won't be at first. As we get better at this, I will become more miserable. Slowly becoming more miserable is going to be the name of my biography, in fact.
Should we be I like it better than the long study. I hated that one.
Four ethyl fluid element. Four. Want to see something amazing? So I just typed the name in. Yeah, but I'm showing you that, like, even with complex names, this is the advantage. If we can wait for Chemaxon. There it is. Well, it's 1, 2, 3, 4, 5, 6, 7 carbons. On carbon 3, we have 2 methyls. And on carbon 4, we have an ethyl. We'll talk about why, actually. There's a reason. There's a reason because graphically, when you look at it from above, it actually does work. You'll see why. Okay, what do we have here? What's our longest chain? And is it this one here? Is there anything funky going on? It's that one there, right? Yeah, you could also, if you wanted to, call that the main chain, right? But it's the exact same thing. So for me, it's easier to think of this as the main chain, right? But actually, just for the sake of argument, so you guys see it's possible, I'm going to call that my main chain. Don't change yours. We will get the exact same answer. All right? How would we number these? Yeah, we said we want the ethane to have the lowest number, right? So for the ethane to have the lowest number, I'm going to call this 1, 2, 3, 4, 5, 6. Now let's talk about my carbon chain. What groups are coming off of it? I've got a methyl group. There it is. What carbon's that on? So what would I call that? 4-methyl. Very good. And what's the other group we have? Yeah, on carbon 3, we have an ethyl, so we would call this 3-ethyl. And of course, the main chain is what? Hexane. And so all together, who wants to give me a try at this name? Again, worst case scenario, you're horribly wrong. Anyone new? Anyone feeling bold, brave? Brave and bold. Do you want to try? Yeah, again, like, listen, have you seen how many mistakes I make a day? Like, the worst case scenario is you make a mistake and everyone goes, oh, yeah, I actually made a mistake, and that's that. Very good. That's exactly right. How am I going to write this 4-methyl, by the way? Dash? Very good. And am I going to put a spacer like that? No, it's all one word. Again, that's its name. That's its name. Some people are named Bob. Some people are named 3-ethyl 4-methyl hexane. I'm thinking about it. I'm worried that poor 3F, which is what I'd call him for short, would have trouble at the airports. I feel like he'd stress people out. And they'd be like, what's your name? 3-ethyl 4-methyl hexane Robert Orlando. And they'd be like, that's a strange name, kid. So, well, exactly, right? Talking about organic compounds at airports stresses poor airport security out. Okay, we're not going to get through this whole thing today, but we're going to get through one more topic. One more. Ready? We feeling bold? Yeah. I feel bold. All right, so I got fired up about this stuff.
What about pi? No.
So, what about pi bonds?
They're gone.
Alondra has already told us that there's no reason 2 carbons couldn't make a double bond, right? Is there any reason they couldn't do that? I can't think of any reason. So now, let's look at ethane. We know that ethane has what structure again? Bless you. How many carbons?
really know what to say.
Okay, so that's ethane. Now, what if instead of a single bond here, I made it a double bond? Well, first question, how many hydrogens are involved now? Hey, side note, what's the hybridization of those carbons? sp2, which means what are these angles? Yeah, 120 degrees. Hey, is this a three-dimensional shape? It sits flat. This is two-dimensional, right? Because it's sp2 hybridization. So interesting things going on here. And to show that this has a double bond, we would name it no longer ethane, but now we call it ethene. And as soon as you see this E, it tells you that there's a double bond. Now, in the case of ethane becoming ethene, where could the double bond go? There's only one place, right? There's only one bond. So this is easy. I just call it ethene. But what if I had a 6-carbon chain? It's going to be hexene, obviously. But if I just said hexene, where could that double bond be? It could be here. It could be there. It could be there. Yep. Yeah, and here's the thing. 1, 2 is redundant. Because obviously if it's on carbon 1, it has to also be on carbon 2. So we number it by where the double bond starts. And again, we're going to number these in such a way that the double bond gets the lowest number. By the way, if there's a double bond and a side chain, we are more concerned about the double bond having a lower number. That gets priority. All right, it's more important. That double bond actually has more effect on this thing's chemistry than that side chain, and that number gets priority. Yeah.
What's the double bond? It's like a you say like 2, 4.
We'll talk. So this would be hexene. What do I have to put in the middle? 1. So this is hex-1-ene. Older naming systems called it 1-hexene. That is passé. That's what you will see it from time to time where they put the number in front, but this is much better. When I learned it, we would have called this 1-hexene. You will discover that as we get to more complicated things, now that they put the number directly in front of the ene, it is much, 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 so much easier. And you should wake up every morning and say a little prayer of thanks to the people at IUPAC and say, thank you, IUPAC, for making naming easier, because it is so much easier than it was 20 years ago. Easier. So much easier. Like, it's way better. You know what? It's like not even a little easier. It's like so much easier. It's much better. Okay. Oh, we haven't got, I know, right? And we haven't even got to Alkynes yet. That's okay. You stole my thunder, but I still like you, Kevin. All right. What would we call this one? Okay. It's a hexane. Only is it a hexane? No, it's not a hexane because it is a 1-ene, right? What else do I have to say about this thing? Great. And what is this? You got it. So this is a specifically 4-methyl. And so who wants to give me the name of this whole thing? Oh, Jade, I've been waiting all day. I'm ready. All right.
4-methyl hex-1.
You got it. That's perfect. 4-methyl hex-1-ene. Bam. There it is. Right? I've always thought that would be like a good car name. Like imagine like the Toyota 4-methyl hex-1-ene.
Oh,
It's got a ring to it and be like, you know, and like they'd call it like the 4-meth for short. Actually, that name will also get you in trouble at the airport. Don't use it. All right? Like don't say my friends call me 4-meth. That's a bad thing to say at the airport. And it will you will totally be hearing that rubber glove snapping sound that you don't want to hear at the other port. So just, yeah.
Because they do Toyota, but they a lot for Toyota, but it's spelled with an E. It's like ELA.
They misspelled it. All right, take a minute, do this one for me. Freeze.
Yes. The parents are probably biochemistry majors. That's how they did.
There you go. We haven't even gotten into esters yet. Okay, so who's done? Look at you guys. I'll give you all a minute more. And I'll say y'all, because I'm folksy like that. Very folksy. That's one of the first things people notice about me.
I thought it was straight.
Yeah,
Well, that is the first thing people notice about me.
Oh, there's a difference.
Yeah, I said like one of, like it's early.
Oh.
Folksy is early, but strong is one. That's like I walk in the room, they're like, that guy's strong. I don't know anything else. And like other people feel the need to show it off with like big muscles and fitness, but that guy, he's just confident. He's like, oh, just they know. I don't need to advertise, right? Like, yeah. Have you ever seen an advertisement for tin cans? No, because everybody needs them, right? They don't need to advertise. Anyway, really buy these empty cans to put products in, companies? You've seen that ad on TV? I think you haven't. I think you're lying to me, Caleb. All right, what do we got? Name this. All right, yeah, you feeling bold? 2 for 2?
2 for 2.
All right, let's see it.
So 4-ethyl 2-methyl hexene. Yeah. I don't know.
We got it. Well done. That was great. Very good. Now, I want to do one with you, and I'm going to leave the other 2 for you. Let's draw this. What does this mean?
2
double bonds. So there's 2 double bonds. Hey, where are they? The first one starts on carbon 1, and the second one starts on carbon. Good. And so we'd show that like this. I'm actually going to draw this with carbons. We will get to 1, 2, 3, 4, 5. Hey, how many hydrogens can this bond to? Yeah, and so I'm actually not even going to draw them. I'm just going to say H2. How many hydrogens can this bond to? 1, 2, 3, 4. None. No bonds left. What about this guy? This one. This fella? 2. And this guy?
3.
Hey, just to keep our brains fresh with it, because it's so important, what's the hybridization state of this carbon? SP. What about this carbon? Yeah, what about this carbon? 2. This one? This one? Very good.
How come the 3 carbons at the end?
Oh, that should say H3. Thank you.
How do you draw that with the skeleton?
Okay, so no, it just, you have to leave a little gap because that's linear. So it would go like that. The little gap tells you that they're connected to one another. And then you would just go one more. So 1, 2, 3, 4, 5. That would be it. Sometimes they will show it just curved like that. That's fine too. It's not as accurate, but it's fine. 1, 2, 3, 4, 5. Both those would be fine. This gives you a better sense of the actual geometry. This is easier to draw. I I am not worried about geometry in your skeleton structures. If you always want to draw them like this and then just throw double bonds in, I'm totally fine with that for now. Yeah. Here's what I want you to do. I want you to try on your own for homework to finish the 4th page of the note, alkynes. We'll take it up tomorrow. So if you start doing it and you're like, oh my God, I have no idea what's going on, don't panic. There's no value in panicking. Do make that voice because it's real good. But
Or
No.
I'll give you all the marks. Yeah, if you can figure out how to like put that voice into writing, you'll get every question right every time. But I want you to try the 4th page and try the homework out, okay? You will find that when you get to the 4th page, it feels a lot like the 3rd page we just did.
Use a rainbow.